So our already next to last speaker is Louis. Sorry about this, Bouckaert.
It's fine.
Okay, it's Louis. Louis is a third-year PhD student at Ghent University, so at least one of the presenters from Ghent University is here. And he actually is under the supervision of Professor Thomas de Beer and Professor Valerie Van Horn.
Yep.
His research is focused on continuous production, and he is focusing on low dose and in particular solving challenges with respect to monitoring these processes. We met in January or February in a small suburb of Zurich and started the work together, which Louis is going to present now.
Indeed.
Great to have you here and great to see what you have done this year.
Indeed. I hope you like it. Thank you very much for the nice introduction, Sebastian. So indeed, I really would like to talk about the inline NER spectroscopy for comprehensive process understanding of semi-continuous blending, specifically for low-dose formulations, actually. So just to give you a short overview, as you all may know, we have a growing market for high-potency APIs, and these kind of APIs, we need to formulate them in a low-dose formulations. What is a low-dose formulations? According to EMA, a drug product is considered low-dose when its API content is equal or below 2%. However, these kind of formulations, they have some issues. We have some issues doing continuous manufacturing, like GSK, Matthew already presented it. For example, that's the reason why Gericke tried to develop actually their semi-continuous blender, because, for example, in a low-dose formulation, in a continuous blending process, your feeders can have some issues with feeding at low throughput, and then your outcome will change, and so it's not that ideal. And that's the reason why they said, okay, maybe we should try to implement a semi-continuous approach. Besides those facts that we have some issues, challenges during production, another fact is that we may have some sensitivity issues with our inline PAT tools, including NAR. So that's the reason why we said, okay, it would be nice if we could implement for the very first time inline NER into the semi-continuous blender of Gericke, and maybe we can try to measure a low-dose formulation. Moreover, we want to have an additional process understanding. Gericke already had some process understanding of their blender, but we really want to improve it. And while we're doing that, maybe we can set up a DOE and to compare different blender settings to each other and define for each blender setting the endpoint of blending. Just to give you a very short introduction, it was already shown, I've explained yesterday as well. Actually, blending exists of two major blending mechanisms. You have macro mixing and micro mixing. So during macro mixing, the major part of powder particles, so the major part of powder particles are moving, and actually macro mixing is the most important one on your blend uniformity. However, you won't have a homogeneous powder blend after micro mixing. So there is an additional procedure, namely micromixing or dispersive mixing, where some final API agglomerates will be delumping and also will be dispersed during blending. So actually, micromixing is a little bit slower than macromixing, and at the end point of micromixing, your blending process should be finished. And it would be nice in our study if we could distinguish macromixing from micromixing as well. In our study, we used a binary formulation because this was just a proof of concept. We wanted to implement for the very first time PAT into this blender. So let's use a binary formulation with just caffeine and lactose with the caffeine as a drug load of 2%. And here, like you saw on the previous slide as well, this is the mini blender of Gericke that we used with 3 different connection ports, with 3 different ports that we used to implement our NER probe. At the right side, as you can see, the Sentronic FO, which we have seen a couple of times the last few days. So the Sentronic FO, therefore we used an acquisition time of 5 milliseconds and an average number of 40. Why did we select 40? We said, okay, we are not sure, because we never done it before, how long the blending process will take. Will it be only a few seconds? Will it be a few minutes? We didn't know, so we said, okay, let's keep the average number as low as possible. Maybe, okay, we have a little bit more of noise, but then we have as much as possible information. So let's keep it as low as possible. And this gives us actually a measurement interval of 350 milliseconds, so 200 milliseconds of measurement and 150 milliseconds of computation. And our study said, okay, it would be nice if we could do a design of experiment. And every run that we will do actually will take 6 minutes. So we will run for 6 minutes. Why 6 minutes? Because we know from literature, and afterwards we could prove it with our data, is that after 4 minutes, our blending process should be finished. So after 4 minutes, we're 100% sure the blend is homogeneous. And the last final 2 minutes, so blended for 6 minutes, the last final 2 minutes, we could use it as a reference. So we used the spectra that we collected during those final 2 minutes as our reference. Just to validate, after those 6 minutes, we opened the top valve actually, and we took 10 powder samples for offline validation, just to prove our blend is homogeneous or not. And actually it was. So we did a full factorial screening design, where we included factors impeller speed, so we varied between 60 and 140 RPM. We had 3 different probe locations, just like we saw on the previous slide, and a fill level between 50% and 100% of the blender. As responses, we defined spectral noise, and of course the endpoint of macro mixing and micro mixing. Which methods did we use to do our data analysis? We used PLS and the moving block standard deviation methods. For our PLS, we included 5 different concentrations into our training data. So the 0.5, 1.5, 2.5, 3.5 and 4.5% concentration. And just as for our DOE runs, we always blended it for 6 minutes, and we used the last final 2 minutes as our reference. So the spectra that we collected during those final 2 minutes we used as a reference. As spectral pre-processing, we did a second derivative followed by SNV. And to train our model, we did some cross-validation. So we said to the model, okay, if you exclude a part of your training data, it has to be all from the same concentration. So for example, the model will exclude, for example, the 1.5% concentration. It was not allowed that it has ever seen the 1.5% before. So we did it like this, and then we could define, based on our root mean squared error of cross-validation, we could define our amount of latent variables that we could include in our model. And the answer on that, we always included maximally 2 latent variables, just to be sure that we were never overfitting. So what was the advantage of PLS? We could predict our API concentration in real time. That was the advantage. However, and that was our biggest limitation, is that PLS, and that's something that we knew already from literature, is that PLS, it is not that robust across different blender settings or process settings, for example, in a tablet press as well. So if you, for example, make your training data at specific settings, in the most ideal scenario, you would do your validation set or your test set at the same settings as your training data. But this would mean is that for each run that we did in our DOE, we should make a PLS model for each run, and that will take a lot of time, a lot of money, and a lot of power as well. So that's something we had to find something on that, and I will explain to you in a few slides how we did it. As a second method, we said, okay, maybe we should do the moving block standard deviation method as well. As you already know from previous presentations from the last few days, how works the moving block standard deviation method. So we said, okay, let's take 3 spectra, so a block size of 3 spectra at a single wavelength. So we took the wavelength of 1670 nanometers, the main wavelength of caffeine, and we calculate the relative standard deviation from those 3 spectra. Then the old spectra is dropped, we include a new spectrum, we calculate the relative standard deviation again. And this we will do in function of time. And you will see, just like you can see here in the right plot, at some point it will drop below a certain threshold, and from the moment it drops below that threshold, the blend can be considered homogeneous. But then we had the question, yeah, which threshold should we use? Because in literature, you find a wide range of thresholds. Sometimes they say 3%, 5%. We were like, yeah, what should we take? And just like we did in the PLS modeling, we said the final 2 minutes were our reference. So let's do the same. In our final 2 minutes, let's take the maximum moving block standard deviation value that we calculated during those final 2 minutes as our threshold. So from the moment it drops below that threshold, our blend should be homogeneous. However, this is another issue that we had, or issue of challenge that we had, is according to the FDA, the mass of a single spectrum should be identical to the final dosage unit of our drug product from our single tablet. Of course, we didn't define the mass of our single tablet, so we said, yeah, maybe we should come up with our own formula to estimate the sample volume. So we had a look in literature, we found a formula that some other people developed for a linear blender, we found some formulas that they used for the tablet press. So let's combine all those formulas to a formula that fits perfectly for the blender, and we were able to estimate our sample volume. Of course, if you will see, we had to make some assumptions. Steve gave us yesterday a very nice presentation about estimating the sample volume. It's not, you have to make some assumptions. For example, what's the penetration depth of your NER light into the powder bed? It really depends on your density. Your density, of course, will depend on the type of powder you're using, will depend on your paddle speed. So, of course, this formula, there are a lot of assumptions in it, and to my opinion, it's not a preferable way, but we wanted to do it just to align with the FDA. And as you can see here, this is a table that we will hopefully publish in our article as well. For example, I calculated it both for the 3 impeller speeds that we included in our design of experiment, and we calculated once for the bulk density and tap density, because we always said, yeah, our density will be between the bulk and tap density, so let's define a range of our sample volume. Like I said in previous slides before, in the ideal scenario, we should develop a PLS model for each different blender settings that we wanted to include in our study. However, that would cost a lot of money, a lot of material. So we said maybe we can use, from each run that we did in our DOE, the final 2 minutes, so the spectra that we collected during the final 2 minutes, and include just the raw spectra into a PCA model, and just have a look, maybe some blender settings result in identical spectra actually. So that's what we did here. So this is the score scatter plot of a raw spectra from the final 2 minutes. And actually, we saw something very nice. The first principal component is describing 95% of all variability. So we were like, okay, all the spectra that are in the blue square, they're almost identical to each other. So we were like, okay, maybe it can be an option to develop just one PLS model at specific settings in this blue square actually, and maybe we can predict other ones from other settings with that same PLS model. That's what we try to do. And actually, we didn't develop one PLS model, we did 3. So we said, okay, let's keep the fill level constant, let's keep the probe position constant, and let's just vary the impeller speed. So just let's make a PLS model at 60 RPM, a PLS model at 100 RPM, and a PLS model at 140 RPM. So actually for the 3 runs that I'm showing there at the right side. And in total, according to this PCA model, we should be able to predict 17 out of 21 runs. And this is one of our PLS models to show you. So this is the PLS model at the lowest impeller speed at 60 RPM. And as you can see, we were quite happy. We can distinguish the different low dose concentrations from each other. What those dots mean, so those outlier values, I will come on to that later on. Okay, this was our PLS model. Those are the offline measurements that we did. And at the right side, you can see our PLS prediction. And as you can see, our predictions are quite okay. It predicts the PLS model predicts it at the start 0%, and that's quite logically because we always included first our lactose, and on top of it we did our caffeine. So the first few seconds it's measuring pure lactose, then it goes up, and then it predicts a stabilized value. But as you will notice, it's just below the 2%. So the reason why that is, we will give it you in a few slides. But the question is, yeah, okay, this is our PLS prediction. When is our blend now homogeneous? Is it at the moment it's stabilized, or is it one of those peaks still there? We didn't know, and that's the reason why we used an additional method, namely the score contribution plot. We said, okay, from the moment it stabilizes at our fixed concentration, we will compare each peak to our final 2 minutes, because our final 2 minutes were our reference. And we compared it to the score contribution plot, and sometimes actually, for example, if you would compare this peak here with our final 2 minutes, you will see in our score contribution plot a high peak at 60-70 nanometers. So we defined, okay, the peak there, this is still an API agglomerate present in our blend actually. And at some point, so this the peak here indicated by the arrow, after that peak, if you compare another small peak with those final 2 minutes, we didn't see any peak anymore in our score contribution plot. And actually, if we compare our PLS predictions with the moving block standard deviation method, so we used a block size of 3 spectra in our moving block standard deviation, and we saw actually it aligns very well. It has, after in this validation run, after 574 spectra, so if you use our measurement interval, after 3 minutes and 12 seconds, our blend was homogeneous. And actually it comes, it's very well aligned to each other, the 2 methods. This is another one that also was in the blue square that I showed you in a few slides before. According to our PCA, we should be able to predict other blender settings with our same PLS model. And actually, indeed, the model predicts at start 0%, and at some points it goes to a stabilized value again. But again, notice it's just below the 2%. And we were like, how is that? What's the reason for that? And I'll give you an explanation later on. This is, I won't show you the 3 PLS model because it's always the same. This is another PLS model. Again, we can clearly distinguish the different concentrations. And at the right side, you can see our PLS predictions. And here, it predicts again 0% at the start, and it goes perfectly to 2%. So we're, okay, this is weird. Here is perfectly 2%, and for our other settings, it wasn't. And also notice, for example, the outlier values, they are not presented here anymore, or almost not anymore. Just to show you, if you compare the PLS to the moving block, here it's a difference of 2 seconds. So let's say always if you compare the PLS to the moving block, we saw maximally a difference of 5 seconds. So actually on a blending process of 3 minutes or 2 minutes and a bit, 5 seconds is not that much actually. And as already told, for our PLS model at 60 RPM, sometimes we saw some outlier values that you can indicate, that you can see there. That like, yeah, what are those outlier values? And again, we just did the same method. We had a look to our score contribution plot, and we saw that those outlier values were really small API agglomerates still present in our blend. So actually at the lowest impeller speed, your dispersive mixing is not completely finished. That's what we noticed. And that may be one of the reasons why our PLS predictions was just below the 2%. So there are really, really small API agglomerates still present in our blend. That's one of our hypotheses. Another hypothesis maybe is that there is a small amount of API. Caffeine is quite electrostatic, that maybe some of the API was sticking to the blender wall. We don't know. And that may be a reason why we just predict below the 2%. Just to have the conclusions of our DOE. So we had a look to our spectral noise, and what did we saw? Actually, at higher impeller speed and higher fill level, our spectral noise decreased. So we had lower noise at those settings. And if we compare this to our formula, this is quite logically, at higher impeller speed, you have a higher sample volume, and at higher fill level, the same, we have a higher density, and this will give you a higher sample volume, and a higher sample volume results in a lower spectral noise. However, we were always able to distinguish the API signal from our spectral noise. Probe location at first sight didn't have that much impact on our spectral noise actually. But then we want to say, okay, we did our PLS predictions. It would be nice if we could distinguish macro mixing just to have process understanding so that we could distinguish macro mixing from micro mixing. So what did we do is we said, okay, from our PLS predictions, from our 17 PLS predictions that we could do, we saw actually at a certain time we reached our stabilized concentration. There were still some peaks, so the blend was not homogeneous yet, but we said, okay, we have reached our stabilized concentration, so let's include that endpoint into MODA as well. And as you can see here, so this is for the 5 liter, the 7.5, and the 10 liter, you can see that fill level will impact your macro mixing actually. And this is the conclusions that we had in MODA actually. Impeller speed and fill level are the most important factors actually, or the only significant factors that were on macro mixing. So the higher the fill level, the longer it takes to finish your macro mixing, and the higher your impeller speed in the opposite way will reduce your macro mixing, which is quite logically actually. For micro mixing, so for macro mixing we used the PLS predictions because we had real-time API predictions, real-time API concentrations. For the endpoint of micro mixing, we said, okay, we can use our PLS predictions again, but to the other side, then we could only include in MODA actually only include 17 runs because we were only able to predict 17 out of 21 runs. So we said, yeah, maybe we should use our second method, or a moving block standard deviation method, because it gives us comparable results. And here, moving block is, of course, it's a quantitative method, so you're not, you not have to be worried about the different blender settings. So actually, that's what we did for micro mixing. So we said, okay, let's include the endpoints of your moving block standard deviation from your different runs into MODA, and those were the results actually. Impeller speed, just similar to macro mixing, a higher impeller speed reduced the endpoint of micro mixing. But fill level, that was something different compared to macro mixing actually. When you increase your fill level is only important when you work at low impeller speed. So at high impeller speed, your fill level didn't affect your blending process that much actually. So as a conclusion, we can say, yeah, spectra could be measured in a very short time. So we only used an acquisition time of 5 milliseconds and an averaging number of 40. We were planning initially to say, okay, maybe we should do some post-averaging to reduce our noise, but actually it was not required. We were always able to distinguish our API signal from the spectral noise. Our effective sample size that we calculated with or estimated with our formula that we developed actually gave us comparable to a final dosage unit. If we compare PLS to the moving block standard deviation method, it gives us quite similar results, so we were happy about to see that. However, PLS was not that robust across different Blender settings. So we said, okay, PLS is quite okay to have real-time API predictions, but if you want to be robust and say, okay, we would really want to compare different Blender settings, the moving block was more preferably, actually. The endpoint of macro mixing, if you have the endpoint of macro mixing, we saw that increasing the fill level had actually extended the time required of your blending process, while impeller speed had the opposite effect. For the endpoint of micro mixing, we saw that increasing the impeller speed reduced the time of blending, and that fill level was only relevant at low impeller speed. So at high impeller speed, it was not that relevant. Thank you very much for your time and for your interest.
Thank you, Louis. Very nice overview about the great work you did since we met for the first time in January or February, doesn't matter. Questions to Louis?
I'm a little just curious, how do you know that, that the blending was completely finished after 6 minutes?
Because we took offline samples and we just measured it. For example, here, this is just some data from our PLS model, actually. So we defined, okay, if the standard deviation, so we took 10 samples, we measured them offline by UVV spectroscopy. We said if our standard deviation is below the 3%, it should be homogeneous. So that's how we validated, actually. So.
Any additional question? Adam?
Nice talk. I was curious, do you think so you mentioned with the PLS models you were challenged by the difference in the impeller speed and fill level. Do you think you could have included that in your DOE to build robustness into the PLS model to account for those factors?
So do you thinking to make one general PLS model then? Or
yeah, one geo.
Actually, I tried. That was our initial plan, and I included an additional slide. So here. So actually we thought, okay, maybe from our 3 PLS models that we did, maybe we should make one huge PLS model to predict. And we always said, okay, actually we can only explain 2 latent variables, also based to a cross-validation, only 2 latent variables should be included. But that's so from the 3 PLS models and 1, you see with 2 latent variables, distinguishing the different concentrations is not that perfect. So actually, if you want to distinguish between the different concentrations, you should include 4 latent variables. But then you see the loading plot of our 3rd latent variable, and this is just introducing some noise, so actually you're overfitting. And then we saw to our predictions that we made that they were not that exactly the same as the individual PLS models. So that we say, that's the reason why we said, let's not include one huge PLS model, but 3 different PLS models.
That makes sense. Thank you.
So, thanks again, Louis. Great talk, great presentation. Looking forward to see the publication next week.